So at the end of the class yesterday, I asked you guys to check your calendars about the date for the midterm. So the tentative date that I had in my syllabus was Friday, March the 12th. And I wanted to make it a 24-hour format, so meaning from the 12th to the 13th. Is that as good a date as any for you, or does anybody want to raise any objections or make any different suggestions? I am not hearing anything. Okay.
What time would that start?
Well, it doesn't really matter to me. Just for the sake of discussion, how about 12 noon to 12 noon?
I should be awake by then.
Should be awake. Okay.
I work both those days, but if I'm the odd man out, then I'll just take one for the team.
Do you want to make a different suggestion? The team hasn't expressed too much, and so
I understand. Would everybody be okay with that Thursday to Friday? Is that doable or is that not doable?
do I hear any complaints about Thursday to Friday? Okay, so if we say Thursday to Friday, so that would be March 11 to 12, I guess. And this period of 12 noon to 12 noon, of course, overlaps with this class. And so we could pick a slightly later time. Do you want to say maybe 2 p.m. to 2 p.m.? 2 p.m. to 2 p.m. on Thursday to Friday, March 11th to 12th. Okay. Anyone want to raise any complaints now? No. Okay, fine with me. Good, let's plan on that. And I will say, I will post 2 practice tests. So I've taught this class 2 times before in the last 2 years. And so I will post the midterms from those 2 years on the Google Drive. And so you can look at those for practice. And maybe I'll recycle questions, maybe I won't. I haven't even thought about it yet. But you can certainly look at them for practice of this style of question that you might expect.
Will we finish chapter 3 before then?
No.
Is that the plan?
No, we will not. And so let's say exam will cover chapters 1 to 2. And so that means homework 1 to 4, I guess. So the one that you're working on now. So yeah, homework 4 is due on March 1st, and I'll get it back to you a few days after that. And so you'll have plenty of time to check your answers from that homework. Okay. And, I say that the exam is 24 hours. I don't really expect you to be working on it for 24 hours, right? I mean, I expect it to be considerably shorter than that. And so I think it's the sort of exam, that you ought to be able to do in, I don't know, hour or 2, something like that. But I'm giving 24 hours so that there won't be any time limitation, right? And the rules for the exam will be open book open notes. You can look at websites. You can use integral calculators, online integral calculators, or software, Mathematica, or whatever you like. You may not communicate with any other people. So, I mean, about the test, you may communicate with other people during that 24 hours, but you may not communicate with any other people about the test. So not with other students in the class, not with former students, not with your friends or relatives or anybody, okay? And so it needs to be, 100% you working by yourself, assisted by books and notes and software, but not assisted by any other humans. Okay, clear enough? Good. All right. Any questions about the test? No. Okay, good. Well, then let's move on then to chapter 3. Okay, so the idea in chapter 3 is that we're going to take a break from solving Schrodinger's equation for specific types of potential energy. And we're going to go more into the mathematical foundations. So it's what the book calls the mathematical formalism for quantum mechanics. And the main purpose of this is to see what aspects of the solution that we've seen so far, what aspects of that are general, right? What aspects of that apply to any kind of quantum mechanics problem, regardless of whether it's one-dimensional or two-dimensional or three-dimensional, regardless of whether it has to do with a particle that is moving in position, or it might be a particle that has some kind of spin states, so internal states of the particle. And so the book here develops a formalism that can apply to all of these possible cases. So it shows the generality of some of these concepts. And also a nice side effect of that is that it gives us a compact notation. Okay, and so there are a lot of places, where you might get tired of writing out a whole bunch of integrals of psi star times something acting on psi, and we're going to get a more compact way of writing all that stuff. And then this will be useful as we go on to quantum mechanics in 3 dimensions, which is what comes in chapter 4 after this. Okay, so the idea here is to make some analogies with math that you might have seen, that you've hopefully seen in your courses on math methods for physics. So especially in the area of linear algebra, okay? And so we want to talk about how quantum mechanics is like linear algebra. And so in particular, how wave functions are like vectors, and observables are like matrices. Okay, so these are some analogies that I want to work out for you. And it takes a few steps. I'm going to start today, but this could go on for a little while. And I'm going to try to emphasize the highlights and skip over the proofs, because the proofs are sometimes less interesting for some students. And so I will try to refer you to the textbook for those kinds of things. Okay, but let's see what I can do. Okay, so let's begin with this idea of how wave functions are like vectors, right? And so what you might remember from a linear algebra class is the concept of a vector space. Okay, so this is like one of the foundations for a linear algebra class. Okay, and the idea of a vector space is that it is a set of mathematical objects that we call vectors with rules for combining them. And in particular, the two kinds of rules that we emphasize the most are rules for addition and scalar multiplication. So that is, you can either add two vectors and get a new vector, or you can multiply a vector by a scalar and get a new vector. Okay. So when I say these terms, are these things that seem sort of familiar to you from the math class that you might have taken? Okay, maybe. All right. So now we want to do the same kind of thing in quantum mechanics. And so we're going to define a particular kind of vector space, which is called a Hilbert space. So a Hilbert space, that's in the family of vector spaces, okay? And it is the set of all normalizable functions of x. Now, here I'm using the word normalizable, okay? I'm not saying normalized, I'm saying normalizable. Okay, so what does that mean? Normalizable means that the integral of the magnitude of the function dx is finite. It's not infinite. Okay, and this is an integral. Well, in the book, the authors of the book are kind of sticklers, and so they always write it as the integral from a to b. Okay, normally we have a is minus infinity, and the upper limit b is plus infinity. So it's the integral from minus infinity to infinity, normally in most cases. Okay, and so we want functions where this integral does not diverge. So it does not diverge in the limits as x goes to plus or minus infinity, And it doesn't diverge in the middle of the domain either. There's no place in the middle of the domain where the function goes to infinity so that the integral diverges. Okay, and now I'm emphasizing, I said normalizable, not normalized. So the integral doesn't have to be 1. So that means that you can normalize a function like this by dividing by the square root of that integral, whatever that integral comes out to be. Okay. And the reason why it's important that the function has to be normalizable but not normalized is that normalizable is a bigger set of functions. And so the set of normalizable functions is a bigger set. It's closed under addition and scalar multiplication. So it's a vector space. When we say it's closed, it means if you have 2 functions, f of x plus g of x, and that's equal to h of x, right? Then if f and g are both normalizable functions, then h is a normalizable function. Right? And so if f and g are both in the Hilbert space, then h is in the Hilbert space. Right? And similarly, if you have, h of x is a constant times f of x. Well, if f of x is normalizable, then h of x is normalizable. The set of normalizable functions is a vector space, right? Because you do these things. You can add or multiply by a scalar, no problem. You still get something in the space. Okay. That would not be true if we were only talking about normalized functions. Okay, so we have this space, okay? And so we want to say that each function, each function, let's say in Hilbert space, we could consider it as a vector. That is, it's an object that we can work with by adding them or by multiplying by a scalar. Okay. Now, one thing that you are accustomed to do with vectors is dot products, right? So when you have 2D vectors or 3D vectors, you know that you can make a dot product. That is, you can combine 2 vectors to make a scalar. Okay, so let's do something like that in Hilbert space. Okay, so for vectors in Hilbert space, that is, these normalizable functions, there's something analogous to a dot product. And the general word for that is an inner product. Inner product is the mathematical generalization of dot product. Right? And it means combining two vectors to make a scalar. Okay, so for Hilbert space, we define the inner product like this. The inner product of functions f and g would be the integral from our lower limit to our upper limit of f of x complex conjugate times g of x dx. Okay, so let me unpack this for you. Okay, so here we just have a notation over here. Okay, so this is our notation for the inner product. Okay, and so it's written as an angle bracket and then the first function, and then a vertical line. This is like the line that you'd use for an absolute value. And so it's a single vertical line. And then the second function, g, and then another angle bracket. And when you're speaking, there isn't really a good way to say it, right? You just say the inner product of f with g. So the definition of that is the kind of mathematical object that we've been using a few times already, well, many times already in this course, okay? That is, we take an integral from the lower limit to the upper limit, and so that is normally minus infinity to plus infinity. And have the first function, complex conjugate, and then the second function. Multiply those things, integrate over all x. Okay, so this is the definition of the inner product on this Hilbert space. So the same way that people define, a dot product of two vectors by saying, we'll multiply the x components, add the sum of add the product of the y components, add the product of the z components. Right? Here's our definition when it comes to these functions. Right? And so for now, you just have to accept this definition, but later on, you'll see why it's a useful thing for doing quantum mechanics. But you can certainly see that your input to this inner product is two functions, that is to say, two vectors in Hilbert space. And the output of this is a scalar, right? When you do this integral, you get a scalar. And it is a complex scalar. Right? It's not necessarily a real scalar, okay? But it's some complex number. Now, with this definition, it matters which of these functions goes first in the inner product, right? Because the first one gets hit with a complex conjugate. The second one doesn't. Okay? So that means then that the inner product of g with f is the integral of g conjugate times f dx. Integral of f with g is the integral of f conjugate g dx. Okay? And are these things the same? No, not necessarily. They might be the same, but they don't have to be the same. Right? And so you can see that the first of these, the inner product of G with F, is the complex conjugate of the second one, right? Because if you take the complex conjugate of what's down here, that is, you take the complex conjugate of everything that's here, okay? So A and B are real numbers, but F might be complex, okay? So the complex conjugate of F star is F. Okay, so that's the complex conjugate. The complex conjugate of G is G star. Okay, and then X is something real. Okay, so we can see that the inner product of F with G complex conjugate is the inner product of G with F. Now we can take an inner product of F with F. Of the same function with itself. So that is just the inner product of F with F like that. So that means we put F in both places, right? So it's F conjugate times F of X dx, which is the same thing as the integral of the magnitude squared of F, like that. This thing is real. It is guaranteed to be real, okay? Because F star times F is the magnitude squared of F. Okay, so that's a real number. And in fact, more than real, this is a positive or zero number. Right? And so this magnitude squared cannot be imaginary. It cannot even be negative. Right? It is positive, or it could be zero if F is zero by itself. Okay, and so we would say that this inner product of F with F is greater than or equal to zero. And expressing things with the notation up there, right? We would say the inner product of F with F conjugate is equal to the inner product of F with F, right? Which is another way of saying that it is real, right? Because it's equal to its complex conjugate. Okay, so this inner product notation, it includes everything I've been telling you this semester about normalization of functions, right? We've done this normalization integral 100 times this semester. And so now we can say, oh, that's an inner product integral. And so let's see, we have this, and what was I telling you? It's greater than or equal to zero. It's zero only if F of X equals zero everywhere. If the function is 0 everywhere, then its inner product with itself is 0. Okay, but if the function is non-zero anywhere, then that place, makes a non-zero contribution to the integral over here, and so then we get a positive result for the inner product of f with itself. Okay, so you good with this so far? This kinds of definitions? This is a lot of definitions and no results yet. Okay, so that's the way it goes. Okay, so then what? Then we can talk about our normalization. Okay, so we say f is normalized if the inner product of f with itself is equal to 1. So that's one concept from the semester that's now written in a more compact way than we were able to do it before. Okay. Another concept from the semester is we were talking about orthogonal functions, like two different states of the harmonic oscillator are orthogonal to each other. So here, the way we write that now is the functions f and g are orthogonal if the inner product of f with g is equal to 0. This is actually quite analogous to what you have with regular two-dimensional vectors or three-dimensional vectors, right? With regular vectors in 2D or 3D, right? We would say u and v are orthogonal, that is, they're perpendicular to each other, if u dot v is equal to 0, right? And so the inner product of functions is like the dot product of vectors in 2D or 3D in this way. Okay, now what? Now we can talk about a whole set of functions. We have a set of functions. I could write it as f sub n. So that means a set of functions, f1, f2, f3, et cetera, et cetera, et cetera. Okay. This set of functions is orthonormal if the inner product of fm with fn is equal to delta mn. Okay, so the Kronecker delta symbol. Okay, so that means, as you know, 1 if m equals n, and 0 if m is not equal to n. Okay, so that's like a set of vectors in 2D or 3D, right? So in 2D or 3D, we might have a set of vectors, say x hat, y hat, z hat, right? Or sometimes people write them as I, J, K. Okay, that is to say, the unit vectors in the x and y and z directions. Right? So this is an orthonormal set, right? This is a set where if you take the dot product of one vector with itself, you get 1. And if you take the dot product of one of these vectors with a different vector, you get 0. Okay? So this is a three-dimensional set that is orthonormal. Okay, so this works with a set of functions. For example, the special solutions for the harmonic oscillator. Okay, that is a set of functions which has this property. Okay? Or the set of solutions for the particle in a box is another set of functions that has this property. Okay, now, if you have any vector, you might want to express it as the sum of vectors in your orthonormal set. Okay, so we would say the set of vectors like this is complete if any other function, any f of x, can be expressed as a sum. F of x is a sum of some Cn times Fn of x. That's the same way that when you're dealing with three-dimensional vectors, the set of x hat, y hat, z hat, or this other notation, I, j, k, is complete because any vector v is one coefficient times x hat, plus another coefficient times y hat, plus another coefficient times z hat. So when you're dealing with three-dimensional vectors, you can describe them, if you want, by a magnitude and a direction. Or you could describe them by their components in the x, y, z coordinate system. Okay? And so it's like that with functions too. Right? We can describe the functions as some coefficient times one of the functions in our complete set. Okay, so there is a special case, a special case is if the set, if Fn is complete and orthonormal. Then you can find the coefficients Cn using Fourier's trick. So this is like what we did a few weeks ago when we wanted to write a function as a sum of signs, right? And so we used a trick where we said, I'll take my function equals a sum of signs and I'll multiply both sides of the equation and integrate. Okay, so now we can see the same kind of trick. Okay, so the general expression for that trick is if I have f of x is the sum over n of Cn times Fn of x, then we take the inner product of Fm with both sides. Okay, so I want to calculate what is the inner product of Fm with F. That is the inner product of Fm with this sum of n equals 1 to infinity Cn Fn. Oops, Fn, like that. Okay, that is the sum. I can take the sum outside the integral in the definition of the inner product. Okay, so that is the sum of the inner product of Fm with Cn Fn. That is the sum. Now I'll pull the coefficient Cn outside the integral in the inner product. So the sum of Cn inner product of Fm with Fn. But this inner product is delta Mn. So in that sum, there is only one term that's not zero, okay? And that is when n equals m. So the only non-zero term is just Cm. Okay, so this tells us what the coefficients are. It tells us the coefficient Cm is the inner product of Fm with F. Okay, so this is a generalization of what we've done a few times in this course, right? When we had some initial condition and we wanted to express it as a sum of the special functions in our solution, okay? So if this is our initial condition, and these are the special solutions of Schrodinger's equation, right? I can express an arbitrary initial condition as a sum of coefficients times those special solutions. Okay? So I've told you this for the particle in the box, and then I told you the same thing for the harmonic oscillator, and I told you the same thing for a free particle, okay? So now there's some general language to cover this concept, okay? And so this inner product language is covering all those things that we have done so far. All right. Now there is a word that I use for this kind of thing. I don't know if it's actually in the book Griffiths, but I'll tell it to you anyway, that the set of Fn's like this is called a basis. Okay. Is that a word that's familiar to you from linear algebra classes? Maybe no. I like that word. I like that word because, you know, it's describes, a set of vectors that lets you express all other vectors as linear combinations, right? And so we could say, if we're doing geometry in 2 dimensions, right, that we have x hat and y hat, right? And any old vector is, here, I'll put it in red. Here's any old vector v is something times x hat and something times y hat, right? And then I could pick a different basis and say, here's x prime and y prime. And any old vector v is a combination of x prime and y prime. So, it's a good concept for doing geometry. And, in geometry, we would say x, y is one basis. And then the blue one, x prime, y prime is another basis. And so now in quantum mechanics, the set of all these functions is a basis for Hilbert space. Now, when you're doing geometry in 2 dimensions, you have count them, 2 vectors in the basis, right? X hat and y hat, right? Or you could change to a different 2, but there always have to be 2 vectors, right? And so the number of vectors in the basis is the dimensionality of the space. So here, this is a 2-dimensional space. Or if we were doing geometry in 3D, we would need to have 3 basis vectors in the X and Y and Z directions. Okay? And that describes a 3-dimensional space. Now, in quantum mechanics, we could count the vectors in our basis, and we would say, oh, here, there's an infinite number of basis vectors or functions. All right, so, for the particle in a box, for example, we had sine of kx or sine of 2kx, sine of 3kx, right? Going up to sine of 1,000,000 kx, 1,000,001 kx, right? The list goes on forever. Right? Similarly, for the harmonic oscillator, right? We had this ladder of states, which starts at the bottom, but it keeps going up forever. So there's an infinite number of states, an infinite number of solutions for the time-independent Schrodinger equation. Right? So that means an infinite number of basis vectors. So in that sense, our Hilbert space is infinite dimensional. Okay, so it's not like a 2-dimensional or a 3-dimensional vector space. It's an infinite dimensional vector space. But that's okay. We can still work with it. And so, we're doing this generalization from 2D or 3D up to infinite D. Are you still reasonably happy? Or, okay. Good, good. Okay. Well, I'm going to do a few more definitions and then we can start to apply them a little bit. Okay. So I was talking about wave functions or functions in general. Okay. Now, the next concept is observables. Okay. So people in quantum mechanics use this word observables. And what it means is, well, just anything you can observe. So a typical thing to observe would be position or momentum or energy. Right? These are all physical properties of a particle that you might be able to observe. Okay, and so in our formalism that I've shown you this semester and I'm developing more mathematically now, observables are represented by operators. So we've talked about operators this semester, and so we know examples of the position operator, x hat, and the momentum operator, p hat, and the energy operator, which is the Hamiltonian, h hat. And this is general, right? This works for anything that you can observe. There's going to be a quantum mechanical operator that represents it. Okay, and now for whatever observable quantity we have, we might want to know its expectation value. That is the average in some quantum state of what you'll get if you'll make measurements of this observable. Okay, so let's consider a general observable, which Griffiths writes as Q hat. Okay, so Q hat means anything, X hat or P hat or H hat, any of those, right? Then we can talk about what is the expectation value. So that is the average of Q. And in the same style as everything else we've done this semester, we're going to write it as an integral sandwich. Okay, so that is, we take the wave function psi star and multiply it by Q acting on psi and integrate dx. Okay. Now, we've been talking about that all semester, but now that you know about inner products, you can say, aha, that's an inner product, right? And so, in fact, we could write it in this inner product notation as the inner product of psi with Q acting on psi, like that. Okay, and we don't need to write a star on the psi here because the star is built into the inner product definition. Okay. And so, it all works consistently. Okay. And so now you can see that the serious mathematical sounding word for this integral is an inner product, okay? So for now, for the rest of the semester, I'm going to stop saying integral sandwich because that's not a real word. And I'm going to say inner product instead because that's the serious word for doing this sort of thing. Okay, so the inner product, it includes the concept of expectation value. And you might say, maybe the reason why people started writing angle brackets for the inner product is that there are angle brackets in the expectation value also. And so that makes a consistent kind of notation. Okay, now one important feature of expectation values in physical quantities is that expectation values must be real. For any real observable thing that you go out and measure in the world, you're not going to get a complex number for it. You have to get a real number. Okay, so that means that we better have that Q equals the complex conjugate of the expectation value. Okay, but this expectation value, we know that is the inner product of psi with Q psi. Okay, and we know that the expectation, that the complex conjugate of that thing is the inner product of Q psi with psi. Okay, that goes back to something I talked about when I first showed you inner products, right? That FG complex conjugate is equal to GF. So here, F is like psi and G is like Q psi. So this must be a property of any operator that represents an observable. Okay, so that is to say, if Q represents an observable, then it has this feature that the inner product of psi with Q psi is equal to the inner product of Q psi with psi for all psi in Hilbert space. Okay, so not all operators in the world have this property, okay? Only a certain family of operators have this property, okay? And the word for this, for operators that have this property is Hermitian operators. Okay, so that means the definition of a Hermitian operator is an operator Q which satisfies this rule. Yeah, psi with Q psi is the same as Q psi with psi. Okay, like that. Right, that's a definition of a Hermitian operator. Okay, this is for all psi in Hilbert space. I will tell you a wrong thing that I believed when I was a student. When I was a student and I first learned about this thing, I thought, ooh, I know where the term Hermetian operator has to come from, because I had studied Greek mythology. And so I knew about the Greek god Hermes, right? Which is the guy with wings on his shoes, right? Like the symbol of the FTD forests, right? And I thought, oh, so Q must be named after the Greek god Hermes because it can sort of fly from one side of the inner product to the other side of the inner product, right? As if he has wings on his shoes. In fact, that was totally wrong. It has nothing to do with the Greek god Hermes, but maybe it'll help you to remember the definition anyway. So anyhow, that's a wrong thing for today. All right, so that is a Hermetian operator. Okay, and so because this is important for operators, we study Hermetian operators a lot in quantum mechanics. Okay, so let me tell you a few things about Hermetian operators. Okay. And then I will give you examples of Hermetian operators. No, I'll do it the other way. I'll give you examples first, and then I'll tell you a few general rules. Okay, so let's do examples first. Okay, so the question is, I'll give you some operators, and we'll say, are they Hermetian or not Hermetian? Actually, it doesn't need a capital letter. It's or not Hermetian. Okay. Okay, so let's think of the operator 2 hat, which means multiply by 2. Okay, and so we could say, what is the inner product of 2 hat acting on psi with psi? Okay, so that is an integral of 2 psi complex conjugate times psi integrated dx. Okay, now we know the complex conjugate of 2 psi, and that is 2 times the complex conjugate of psi, right? And so this is the integral of 2 psi star times psi dx. Well, you know, in an integral, you can move a factor around. So this is the same as psi star times 2 psi dx. Oh, and then this thing is the inner product of psi with 2 hat acting on psi. So that's what we needed to prove, right? So that proves that, you know, therefore 2 hat is Hermetian. Okay, what about another example? Okay, how about the example of I hat, which means multiply by I? Okay, well, if we want the inner product of I hat acting on psi, inner product with psi, that means this integral of I psi complex conjugate times psi dx. Okay, now what's the complex conjugate of I psi, right? Well, in a complex conjugate, we have to take the complex conjugate of everything. Okay, so we take the complex conjugate of I times the complex conjugate of psi, and that multiplies psi and gets integrated dx. And now, if we try to rearrange things, this is the negative of psi star I psi dx. So this is the negative of the inner product of psi with I hat acting on psi. So it's not true. So this is not Hermitian. Okay. And in general, that works whenever you're multiplying by a constant, right? If the constant is real, Hermitian. If the constant is not real, not Hermitian. Okay, let's make a more interesting example. Okay, how about x hat? That is, multiply by x. Is that Hermitian? Well, if we have x hat acting on psi, inner product with psi, that's our integral of x psi, complex conjugate, times psi, integrated over x. The complex conjugate of this thing is x times psi star, because x is real. Okay? So this is the integral of x psi star psi dx. Oh, well, okay, I can rearrange the factor of x there. And this is the same as the inner product of psi with x acting on psi. Okay, so yes, this is Hermitian. And good, because I think x hat represents an observable, right? So that story is consistent. Okay, let's do one trickier one. Okay, how about the example of d by dx hat? Okay, that is an operator to take the derivative of a function with respect to x. Okay, that's a little trickier, but we can do it. So if we have that derivative operator acting on psi, inner product with psi, that is the integral of d psi dx, that derivative complex conjugate, times psi integrated dx. Okay. That is equal to an integral of the derivative of psi star times psi dx. Okay, now we want to compare this with an inner product of psi star with the derivative of psi. That is, we want to have the derivative acting on the psi instead of the psi star. The way we can do that is integration by parts, okay? Similar to what we've done a few times earlier in the semester, okay? So we're going to integrate by parts. Where we say u, that's psi, and dv is d psi star dx times dx. Okay, so du is d psi dx times dx, and v is psi star. So this integral comes out to be psi star psi evaluated from minus infinity to infinity minus the integral from minus infinity to infinity of psi star d psi dx dx. Now we have this set of terms at the boundary. You know the story with this because we've done it a few times this semester, right? That this product has to go to 0 as x goes to plus or minus infinity. That's the only way that the function can be normalizable, right? And we have just normalizable functions in Hilbert space. Therefore, this integral, the integral here, is equal to the negative integral over there. And that integral is negative inner product of psi with the derivative operator acting on psi. So this is not Hermitian. Okay. Now how am I doing on time? Oh, I'm running out of time. Okay, I'll stop for today. And I will continue on Thursday with some more examples of Hermitian and not Hermitian, and then go to some other general principles from that. And hopefully we can get to calculating stuff. Okay, let's take a break here. And I will certainly answer questions about all this stuff, including if any of you have the question like, why do you care about all this stuff? You know, hopefully there will be a good answer for that. So then I'll see you on Thursday. Okay, bye.